So in this question we're asked to consider a second order boundary value problem, a reasonably simple one. We've got 2-point boundary conditions, and the first part of the problem is what equation must omega satisfy in order for omega lambda equals omega squared to be a positive eigenvalue. Okay, so what we're going to do is solve the differential equation where lambda equals omega squared, it's positive, and see when we couple the boundary conditions what sort of what equation needs to hold in order to get non-zero or non-trivial solutions. Okay, so if lambda is omega squared and it's positive, this the characteristic equation is pretty reasonably simple. You're going to get the characteristic equation is going to be something like r squared plus lambda equals 0. So we're going to get complex solutions with 0 real part. So in that situation, the general solution to our differential equation is this. Okay, so now let's bring in the boundary conditions and look for non-trivial solutions. Okay, so the left-hand boundary condition, we take our general solution, we differentiate it. When we differentiate cosine, we're going to get a sine, which will go to 0. If we differentiate sine, we'll get a cosine, which will go to 1 at x equals 0. So the omega will come to the front, and we'll get the following. Now in this setting, omega is positive, so that bottom equation here holds for b equals 0. Okay, so certainly one of our general constants is 0, but what we want now is to get the other constant a non-zero. So the other boundary condition is this one here. So we differentiate, plug in x equals 1, so we're going to get something like the following. Okay, so b 0. So if I differentiate that, I'll get something like minus sine, and I plug in x equals 1, I'll get something like this. Okay, and then taking away this thing at x equals 1, I get the following. So I can factor out those minus a. I get something like this. Now, we don't want a to be 0, otherwise we get the trivial solution. So we want what's in this bracket to be 0. Okay, so what does this mean? If we just sort of rearrange that and sort of use sine over cos is tan, you'll get the following. So that's the equation that omega has to satisfy in order for lambda equals omega squared to be a positive eigenvalue. So in the second part, we're asked to show that lambda equals 0 is not an eigenvalue of our problem. So essentially what we can do is just go to our original differential equation, plug in lambda equals 0, and show that you only get the trivial solution. Okay, so that's pretty straightforward. Okay, so the solution to u double prime equals 0 is just going to be something like ax plus b or something like that. So what we can do now is use the boundary conditions to show that A is 0 and B is 0. Okay, so U prime of 0, that's just going to be basically A. So A is 0. And U prime of 1, well, basically if A is 0, we're left with a constant B. So if I differentiate B, I'm going to get 0. Okay, so B equals 0. So we only get the trivial solution. Thus, lambda equals 0 is not an eigenvalue. In this part of the question, we're asked to show that the problem has exactly one negative eigenvalue. So what we are asked to do here is to show that there's one and only one negative value of lambda, such that the boundary value problem has a non-trivial solution. So I prepared this solution earlier, so let me just step you through it. So imagine omega is negative here. We solve this problem like we did before, and it actually makes a lot of sense to let lambda equal negative omega squared, where omega is positive. That way, when we write down the characteristic for this problem and solve it, we get sort of, there's no square root signs in our general solution. Okay, so if lambda's negative here and minus omega squared, well, the roots to our characteristic equation are going to be positive omega and negative omega. They're going to be real. So our general solution is just a linear combination of exponentials. Okay, well, if we use the left-hand boundary condition, well, this is what we get. The exponentials go to 1. So you can see that we can factorise. Now, omega is not 0 here, so A minus B is 0, so that means A equals B. And then if we use the other boundary condition by taking this and differentiating it, and then taking away this evaluated at x equals 1, I'll get the following. And then if you say, replace B with A and do a bit of factorisation, you get down to this. And I can rearrange that. Now this here is hyperbolic cot. So essentially this is the equation that we're interested in. And on the right hand side, I've drawn the graph just very roughly. The graph of hyperbolic cot, and here's the graph, say y equals omega or something like that. Now, in the right hand half of the in the right hand half of the picture, you can see that there's one and only one intersection. Okay, remember in this equation, we're looking for positive omega. Okay. So you can see that there's the intersection. There's one and only one intersection. So there's one and only one positive omega that satisfies this equation. Okay, that means that, well, for lambda equals that minus omega squared, there's one and only one negative value of lambda, such that this problem has a non-trivial solution. Okay, so our conclusion then would be, because this intersects once and only once in the sort of positive half of the picture, there's one and only one point of intersection, hence there is one and only one negative eigenvalue lambda, because lambda equals negative omega squared. Now we're also asked to give an approximation for the jth positive eigenvalue when j is large. And again, I'm going to do this graphically. Yeah. So from our work on part 1, this is our equation of interest. Okay? So essentially what I've done with this sort of graphical approach in part IV is to sketch the tan function, sketch -1 on omega, and then see where they intersect. So here's one I created earlier. Now this is another command, okay? This is not related to this graph. Okay, so the green curve here is minus or -1 on omega. The red curve is a sort of very elongated tan curve. And you can see what happens is that, all right, so if you look at the first intersection and go up to the axis, it's sort of, it's reasonably close to pi. And then if you go and look at this intersection, it's getting a bit closer, and then a bit closer, and then a bit closer. So from that graph, what do you think the eigenvalues will approach as we sort of move far to the right? Yeah, so yes, who said J pi? Yeah. So you can see, at all these, basically the intersections are getting closer and closer to where the red, the curve cuts the axis, which is just multiples of pi, right? So now, I'm sure you can do lots more than come up with this thing. You can probably come up with a far more precise approximation. But I'm just keeping it very, very simple.